Watcher glitches. So, in the spirit of working out loud, I've read this blog post from Flare Networks on consensus learning a couple of times now. Consensus learning, harnessing blockchain for a better AI. And I also started reading the paper, which I'll show you in a minute. But I thought I'd just read this out for whoever's interested, really, and then show you how I'm kind of trying to get my head around some of these concepts and what I think about them. So let's dive in. Consensus learning, harnessing blockchain for a better AI. Flare Research's latest paper introduces a new approach to artificial intelligence, AI. Combining AI with blockchains leads to safer and more accurate AI. Consensus learning, CL, enables collaborative AI across a spectrum of applications, enabling the development of more accurate and robust AI models. CL is particularly suitable for AI integration in data-sensitive sectors such as healthcare or finance, thereby improving decision-making processes and enhancing overall operational performance and efficiency, which in turn can result in lower cost for services to the end consumer. This can result in significantly better patient care outcomes, more accurate financial analysis, or enhanced fraud detection, among other benefits. In contrast to most existing implementations of AI and blockchain, which enable access to centralized machine learning models through ML through the blockchain, CL leverages blockchain to create decentralized AI models. Motivations. In recent years, there has been a growing emphasis on distributed environments, where data and computational resources are spread across multiple devices. This shift is prompted by the requirements of modern foundation models, such as large language models and computer vision models, which demand substantial amounts of data for processing. In this distributed but centralized setting, decentralization emerges as a fundamental need driven by several key motivations. Centralized models present inherent risks by relying on a single trusted party, which confine their use mainly to single enterprise settings and constrain their broader adoption. Moreover, these architectures not only increase the vulnerability to potential attacks or system failures, but also raise concerns about data privacy and security. Conversely, decentralized methods present a distinct advantage. They enable users to develop personalized local models tailored to their specific requirements and preferences, whereas centralized approaches often lack the flexibility required for such customization. Amidst these limitations, consensus learning emerges as a decentralized ML solution offering greater resilience, privacy, and adaptability while mitigating the inherent risks associated with centralization. Benefits of consensus learning. Consensus protocols are essential to the security of decentralized ledgers and protect blockchain networks from malicious attacks. Harnessing consensus mechanisms for AI has many benefits, among which we highlight the following. Increased performance. CL methods benefit from the data of each of its ensemble contributors, reducing bias and enhancing models' ability to generalize on unseen data. CL can also lead to more accurate AI as compared to centralized methods, primarily due to blockchain's ability to incentivize collaboration, leading to a greater proficiency in combining diverse insights from diverse models. This is achieved via multiple local aggregations, where each participant assesses the predictions of neighboring models and integrates them for better accuracy. This is one of the first instances where AI can gain significant advantages from blockchain integration. Security. In the presence of malicious actors attempting to introduce hidden objectives, the integrity of CL models remains uncompromised due to the built-in safety features of consensus mechanisms. This ensures that AI systems refrain from generating deliberate harmful predictions or unintentional inaccuracies, both of which are the hallmarks of malicious AI. Consequently, CL addresses a major concern within the AI community, protecting AI from exploitation for detrimental purposes. By upholding the integrity of the collaborative learning process, CL instills greater trust and confidence in AI systems, paving the way for their responsible and ethical deployment. Data privacy. In CL, neither the underlying data of the network participants nor their individual models are shared at any point. In fact, there are no malicious attacks on the network capable of compromising data confidentiality, since data remains stored locally. Preserving privacy not only encourages collaboration, but also preserves competitiveness. In this regard, CL enables data monetization through AI, especially for sensitive or commercial data such as healthcare, overcoming previous challenges encountered in centralized environments. Full decentralization. Data and computation resources are spread across a network of participants which communicate without relying on a single central server. The necessity of decentralization is prominently visible in the modern ML applications due to the demand for vast amounts of resources and the increasing complexity of ML models. Decentralized ML emerges as a more fitting solution for preserving data privacy and ensuring security. Efficiency. The learning process has low latency and requires much less computation time, energy, and resources as compared to the other state-of-the-art decentralized ML methods. This makes CL particularly suitable for real-time applications, where quick decision-making and efficient resource utilization are paramount. How it works. Consensus learning enhances ensemble methods through a communication phase, where participants share their model outputs until agreement is reached. CL is a two-stage process that can be implemented as follows. Individual learning phase. Each network participants develop their own model based on their private data and other publicly available data. This can range from building a model from scratch, using a large pre-trained models, and fine-tuning them to their needs. Crucially, a participant will never be required to share sensitive information about their data model. Once the training is complete, participants will prepare their initial predictions for a testing dataset. This can be a dataset disclosed through a smart contract, or alternatively, participants may propose new testing data points through a proof-of-stake mechanism, for instance. Communication phase. Participants transmit their initial predictions within the network according to a consensus gossip protocol. During these exchanges, participants continuously update their predictions to reflect the assessments of the other network participants, as well as the confidence in their own predictions. Additionally, a participant can monitor the quality of the predictions received from the rest of the network and use this to improve decision making. At the end of this phase, participants come to consensus, on the decision deemed optimal for the information available in the network. This phase is then repeated for any new data inputs. So in this figure here, we'll go through the caption. As an example of how CL works for binary classification task. In the first stage, participants develop their own models based on their own data and possibly other data willingly shared by other participants. At the end of this phase, each model determines an initial prediction presented by the hollow circles for any inputs of the testing datasets. B. In the communication phase, participants exchange and update their initial predictions eventually reaching consensus on a single output, represented by the filled circles. This phase is repeated for any new data. So here we've got these data sets which are never shared, or if they are shared, it's agreed that they're shared. So this chap here is using his own data set and shared data set, as is this one, but it's willingly shared. Otherwise, it's entirely private data that they're using. They're not sharing it, and they only output their predictions. They're not sharing their the data at this stage. It's only the predictions. And then in the communication phase here, we can see that there's a demonstration of how the predictions can change based on the predictions from the other network participants. Strictly speaking, the algorithm described above refers to a supervised ML scenario. Specifically, this is a setting where the training datasets are already labeled and where the algorithm makes predictions for the labels of new unseen testing data. However, CL can also be adapted to self-supervised or unsupervised ML problems, where participants only have access to partly or completely unlabeled data. The objectives of these models are slightly different, requiring participants to employ different techniques during the individual learning phase. Nonetheless, the communication phase would proceed in a similar manner to the description provided above. How consensus learning sets itself apart. The idea behind CL is that of efficiently combining knowledge in the form of AI models from multiple sources without sharing any sensitive or valuable information or intellectual property. This approach is designed to protect confidential information while also ensuring resilience against potential risks posed by malicious entities. CL builds on the highly successful ensemble learning paradigm, which provides powerful techniques for merging multiple models into a single one. Ensemble methods rely on the principle of wisdom of crowds, leveraging the collective knowledge of a crowd to surpass that of any single member. Several blockchain implementations of AI services have emerged in recent years, showcasing innovative approaches to integrating AI with decentralized networks. For instance, BitTensor facilitates AI inferences model output with its domain-specific subnets by weighting the predictions of the miners through a game-theoretic mechanism. Flock.io offers a platform for federated learning, a different type of distributed learning, albeit with a centralized aggregator, utilizing the blockchain for validating model updates and rewarding participants. Another example is Ritual, which effectively operates as a marketplace for ML models through its Infernet protocol, where requests for running a specific model are sent to the model owner. CL sets itself apart through its distinct aggregation method, wherein the predictions of the individual models pass through a secure gossip protocol for the purpose of reaching agreement. As such, CL leverages blockchain to create decentralized AI models, whereas existing implementations enable access to centralized ML through the blockchain. The focus is on enabling more accurate and secure AI through collaboration, whilst at the same time allowing entities that hold private, often sensitive data to join the system, while ensuring the confidentiality of their data. In summary, consensus learning presents a groundbreaking opportunity to implement machine learning directly on decentralized ledgers like blockchains. With this initiative, we witness the emergence of a novel approach where blockchain technology can fundamentally improve existing AI tools. This opens up exciting possibilities for innovation and secure collaboration in traditionally data-sensitive sectors such as healthcare, setting the stage for the adoption of collaborative ML techniques. Moreover, The resilience of CL methods in the face of malicious factors fosters greater trust in AI systems, fortifying their reliability and integrity. So yeah, I mean, this is strikes me as being pretty novel and a genuine use case where blockchain can improve AI and kind of alleviate some of the concerns again around security, efficiency, and the other factors that the blog post mentions here, privacy. Again, it's great to see Flare networks demonstrating that decentralization is in their DNA. This is what I love about Flare networks. And just a quick reference to the actual paper here. I have to confess, I have not read the whole thing, and some of the mathematics is beyond my ability to assess, at least unassisted and without a long amount of time. And I just don't have the time. But I started reading this, I got about halfway through. And then I do what I normally do, which is just use AI to help me get through the paper. So my main questions is like, to me, this strikes me as a novel method. So I pushed it into Claude and asked Claude how novel is this method. Hopefully it's clever enough to go through all the notes. And this is what Claude has to say to the question of, is consensus learning novel? Based on the paper, consensus learning appears to be a novel paradigm for decentralized ensemble learning, but there are some related existing approaches. Federated learning is a prominent distributed learning paradigm where nodes train a model collectively by sharing only local model updates to protect data privacy. However, federated learning is still vulnerable to malicious behavior and relies on a central server, as was stated in the blog and the paper. Meta-learning models combine the outputs of base learners in a secondary training round, similar to the first stage of consensus learning. But the communication phase in consensus learning does not involve retraining and uses local aggregation rules instead. Okay, I need to dig into precisely what that means. Knowledge distillation-based federated learning algorithms communicate only predictions on an unlabeled test set to improve local models, which is similar to consensus learning. However, for most research focuses on centralized knowledge distillation algorithms. Again, centralization creeping in there. Consensus algorithms have been used in distributed neural networks where agents share the same neural network and aggregate local updates based on network topology. This is reminiscent of peer-to-peer federated learning. Blockchain proof of learning mechanisms have nodes submit ML models that are ranked by randomly selected validators, but these currently lack the collaborative problem-solving utility of consensus learning. So while there are some conceptual similarities with existing approaches, the paper argues that consensus learning, by combining consensus protocols with ensemble learning in a fully decentralized manner, provides a novel paradigm that addresses limitations of competing methods in terms of data privacy, Byzantine resistance. I said Byzantine in American ways, Byzantine resilience, communication efficiency, and collaborative utility. The theoretical analysis and results are tailored specifically to this new paradigm. So it certainly strikes me as a novel way of the blockchain applying to AI, and really fascinating one. Again, demonstrates Flare networks thinking forward and identifying use cases for decentralization, and what is important about decentralization and the resilience that it can offer to multiple different segments. I mean, I remember, back in the early days, blockchain was like the laser. It was a great invention looking for a use. And I'm just thinking that right now, Flare networks are finding lots of very good uses for the blockchain. So yeah, very excited about this and monitoring it very closely. I hope this was useful for everyone else as well. I'd love to hear critiques of this paper. I think if you are in the field of AI and aware of approaches that are similar to this or have critiques of this approach, I'd love to hear about. Thanks a lot, guys. Later, glitches.